Good morning, everyone. I'm Diego Russo, and today we're going to explore something exciting, the just-in-time compiler recently added to CPython. Now, before we start, a quick raise hand exercise. Raise your hand if you know what a JIT is. That's good, right. Raise your hand if you knew that CPython has an integrated JIT in the runtime. That's good. Now we see the pro users here. Raise your hand if you ever used the CPython JIT. Oh, very few, yes. That's expected, by the way. Okay, so independently of your level of understanding and experience, I think this presentation is going to be useful in any case. So this is the official Python runtime, finally growing a JIT. And it's happening inside the interpreter we use every day. I'll walk you through how it works, what it looks like, and how we can use it. We're going to look at Python internals, including bytecodes, JIT mechanics, even a bit of assembly and machine code. So if you're not used to that, don't worry. I'll keep things kind of on the big picture, but just, you know, we are going under the hood. I've been writing Python for almost 2 decades, and I spent the last 14 years at ARM, where I work as a principal software engineer in the runtimes team. I'm also one of the leads of the Python Guild at ARM, which is a company-wide community with over 1,500 members. I've been contributing to CPython and its ecosystem for the last couple of years, and focused mainly on performance and internals. In particular, I spent last year working on the experimental JIT compiler, and just a couple of months ago, in May, I became a core Python developer. Thank you. So what is a JIT compiler in the context of Python? A just-in-time compiler is a component of the runtime that identifies frequently executed portions of the code, what we call hot code paths, and compiles them into native machine instructions while the program is running. This gives us the best of the both worlds. On one side, we have flexibility of the interpreter execution for most of your code, and on the other side, the performance of compiled code for the parts that matter the most. In CPython case, the JIT is a tracing JIT. It observes how the code behaves. I know that you don't see anything there. Well, I keep talking. It observes how the code behaves during the execution. It builds traces which are linear paths through the control flow, and at the end, it compiles those traces into fast native code. Where was I? So it observes how the code behaves during the execution. It builds traces which are linear paths through the control flow, and at the end, it compiles those traces into fast native code. These traces are not general-purpose functions. They are specialized paths that avoid the checks and in the interpretation. Once the JIT takes over, we completely remove the interpreter overhead for that specific path. So let's talk about the strategy that CPython uses to implement its JIT. It's called copy and patch. This is quite different from the heavyweight JITs that we build, that builds and optimizes entire functions on the fly, for instance, using LLVM or some custom IRs. Instead, CPython approach is simple and pragmatic. For every micro-operation, for example, things like loading a variable, doing an integer multiplications, or jumping to the next iteration, the JIT has pre-compiled machine code stencils already built in. When a trace becomes hot, the JIT copies these code stencils into memory, and then it patches them with a runtime-specific values, things like constants, memory offset, jump targets, and etc. These patch fragments are then linked together and executed instead of interpreting the original bytecode. There are some important benefits to these designs. It avoids the need for a full dynamic code generator, which reduces the complexity. It's portable. That means it works cleanly across platforms, including ARM and x86. And it's maintainable. It just reuses known good code paths and is specialized page trace rather than trying to compile some random Python logic. So it's worth asking, why is CPython adding a JIT now, and what had to happen first? So in 3.11, CPython introduced a specialized interpreter. It runs regular bytecode, but as the program executes, it rewrites the hot bytecodes on the fly with more specialized versions. This mechanism gathers runtime data, things like types, branch outcomes, and which code is hot. All this information are critical for a later compilation. In 3.12, a new DSL has been introduced for generating interpreter code. This helped manage the complexity, removed a lot of boilerplate code for things like stack manipulation and reference counting. We now have a single source of truth to generate multiple tiers of interpreters. And in 3.13, a new micro-op interpreter was added. It lowers specialized bytecode into micro-ops, which are simpler and easier to optimize. This new pipeline detects hot code and runs it more efficiently. The first implementation of the JIT is in the code base. And now, in 3.14, the experimental JIT is more accessible to users. It improves micro-op performance, and it adds infrastructure for better code stencil generation. So the JIT is not just a shortcut, but is actually the result of many years of foundational work to modernize the CPython execution pipeline. So let's go more in details on how the JIT works in 3.14. So we're going to see the high-level execution pipeline in 3.14 from the Python source code all the way down to machine code. It starts, as always, with your Python source code. The CPython internal compiler parses it into an abstract syntax tree. It builds a control flow graph, and it applies some basic optimization. Eventually, it emits bytecode. That bytecode is then executed by the interpreter. While running, it collects profiling information, what types are used, which bytecodes are hot, and how values flow through the code. Based on that, the interpreter starts rewriting bytecode structures with more efficient specialized versions, the ones that assume specific types or behavior. Then, when a loop becomes hot enough, CPython lowers the specialized bytecode into micro operations. These are low-level fixed-purpose instructions designed for easier optimization. The next step is to take these traces of micro-ops and apply further simplifications to produce an optimized micro-op trace. And finally, the optimized trace is passed to the JIT, which uses the copy and patch technique. It assembles native machine code functions by copying code snippets for each micro-op and patching with the runtime details. That native trace now completely bypasses the interpreter for this part of the program. It's faster and it's running real hardware instructions. Now that we've seen the big picture, let's follow a concrete example through the entire execution pipeline. We have a function here that we're going to follow in details. It's called sum squares. It takes n as an input. It's a very simple loop. There is a total is initialized. It iterates over a range of n, and it adds I times I to the total. And then finally, it returns the result. So despite being simple, this function contains all the right ingredients to demonstrate the CPython JIT pipeline. A loop which can become hot. There are integer operations that can be specialized, and the structure that can be easily lowered into micro-ops and optimized. Let's focus only on the for loop. And this is the respective bytecode for the cycle. before any specialization or tracing happens. The compiler emits general-purpose opcodes, things like for iter, which controls the for loop over the range of n, load fast for loading variables like I and total, and two generic binary ops instructions, one for I times I and the other one for the plus equal. These instructions are intentionally broad. For example, binary op handles any Python multiplication or addition, whether it's an integer, a float, a list, or even user-defined objects. This flexibility is great, as we saw in the previous talk, but it's not ideal for performance. In a moment, you'll see how CPython rewrites some of these instructions at runtime based on observed types to make them faster. As the function runs, CPython interpreter starts rewriting the bytecode based on what it observes at runtime. For instance, if n is an integer and it sees that I and total are always integers, it can replace the generic binary op instruction with a faster type-specific variant. And in this case, binary op star has been replaced with binary op multiply int, binary op plus equal, with a binary op add int. And for iter might become for iter range because we are assuming that we are iterating over a range object. These specialized instructions are faster because they skip dynamic type checks, and they assume the type, and they are correct as long as the runtime guards hold. There are two things to highlight. These changes are done automatically and incrementally. The interpreter evolves as your program runs. And there is no need to recompile or restart. It's all dynamic and happening at runtime in background. So once the bytecode has been specialized and the function runs enough times, CPython takes the next step. It lowers the bytecode into micro operations or micro ops. And then basically each bytecode instruction is broken down into multiple micro ops, which are simpler operations with a well-defined behavior, such loading a variable, performing an integer multiplication, or storing a result. We'll see how this bytecode will be lowered into micro-ops. This is a small animation that basically we take every bytecode instruction, and this is kind of exploded into micro-operations. And what you see here is a trace, which is basically a straight line execution path extracted from the running function. It contains only the operation that actually happened. There are no branches and no abstractions. So once the bytecode is lowered into micro-ops, CPython doesn't immediately hand that off to the JIT. Instead, it performs a few simple but effective optimizations on the trace that you can see that here. In this example, some of the generated load fast and store fast instructions have been replaced with a more specific optimized variants like load fast 1, store fast 2, and so on. These aren't just name changes. They reflect the actual memory slot numbers in the local variable array. For example, load fast 1 means load the value from local variable slot 1. Store fast 2 means store a value into the slot 2. One more optimizations that can happen during this phase is the removal of redundant checks or guards. For example, if the JIT inserts a type check to ensure a value is an integer before a binary op, and then it sees that the same check is already occurred early in the trace, it can simply remove it. This kind of redundancy is common when we have a loop or a block that performs similar operations repeatedly with the same types. The result is a cleaner, tighter micro-op trace, which is faster to compile and to produce better machine code. This step is important because it balances performance and simplicity. We are not doing a full-blown compiler optimization passes here. It's just enough to make the generated code smaller and faster without adding too much overhead. So once we have an optimized micro-op trace, CPython takes the final step. It generates native machine code. This is done using the copy and patch approach we introduced earlier. For each micro-op, there is a pre-compiled machine code template, which is a short sequence of machine code instructions that implements that specific operation. The JIT copies these templates and patches them with the runtime details, like instructions, address relaxation, memory location, and jump offset, and etc. Now we see how these micro-op trays will be converted in a machine code. Again, this is another small animation that basically it shows how we consume all the trays and then will be replaced with a native machine code. And once patched, these pieces are all linked together into a single executable block. That block is then called directly, and this is what bypassing the interpreter. What's clever here is that CPython avoids building a full code generator. It just reuses fast machine code fragments and stitches them together efficiently. This makes the system portable and much easier to maintain than a traditional JIT. So with the next set of slides, I want to explain how a template is generated by a micro-op implementation at a build time and how the patch works at runtime. Just to be explicit, by build time, I mean when we compile CPython. And by runtime, of course, I mean when we run our Python application. So let's take a closer look at the _set_IP micro-op. Its job is to update the instruction pointer of the frame. Very easy. And this is literally the code that implements it. We load the value of the operand, which is a pointer to the next micro-op instructions, and then set as the new frame instruction pointer. When the micro-op set IP is selected for JIT compilation at build time, so when we compile CPython, its implementation is wrapped inside the standard C function template, like this one that you see here. This function is not for the entire trace. It is designed to execute a single micro-op, with all the necessary runtime context. It takes 3 arguments: the current interpreter frame, the stack pointer, and the thread state. These are passed in because any micro-op might need access to them. For example, in this case, set IP needs only the interpreter frame. And inside the function, you see several patch value placeholders. These are the fields that will be patched at runtime. These are things like the actual micro-op to execute, its operand, the target address, or the continuation point. In the case of set IP, the operation is simple. It sets the frame instruction pointer to the value of operand 0. The operand, which is the new instruction pointer, will be patched just before execution. So when we build, we don't know what the operand is. So once patched, this becomes a fully functional micro-op execution unit, ready to be called from within a trace. And this is what the JIT wrapper for set IP looks like after it's compiled, but before it is patched. It's a short sequence of arg64 instructions that implement the core behavior of set IP, updated the frame's instruction pointer, and jump into the next micro-op. Let's walk through the instructions. The first instruction is an address page. This loads the page address of the JIT operand 0 symbol, which will be patched later with the actual value. The second instruction is a load register. It loads the full 64-bit operand, which is the new instruction pointer, into register X8. And the third instruction is a store register. It stores that value into the frame instruction pointer field. Now, on arg64, X20 holds the frame pointer, and the offset 038 correspond to the instruction pointer field in the frame. The last instruction is a branch instruction, and that basically it jumps to the next micro-op functions. gContinue should be patched with the correct continuation target at runtime, because at this time we don't know where we need to jump. You can see also the relocation tags. These are marks where the runtime linker, or like in this case, the patching logic, will fill in with the real operand and continuation values. So even though this code looks static, it is actually just a template, or by other terminology, is a stencil that can be executed once it has been patched. And this is the C function that defines how the machine code for setup is emitted at runtime, so when we actually run our Python code. It lives in the CPython JIT backends, and it sits next to other hundreds of emit functions. And we have this function, one for every micro-op implemented. For this presentation, I chose a very simple one to represent, but the other micro-ops are fairly big. So the code body array that you see here is the binary representation of the instructions that we saw earlier. Is the same arg64 sequence that performs _set_ip. And this is what we call the stencil. It's a small precompiled machine code template that implements the logic for a single micro-op. When the JIT needs to emit setIP, it simply copies this array into executable memory and patches in with the right operand values. So rather than generating new code every time, CPython uses this reusable stencil to keep the JIT simple, fast, and portable. This specific function does three things. It patches the operand using patch64, which writes the actual runtime value. It copies the stencil into the code buffer with memcopy. Then it calls this function, which is called patch arg6433rx. And this is where the things are, where it gets a bit clever. That specific function specifically tries to relax the code. It means that if the operand is close enough to the instruction pointer that we're executing, the patcher can rewrite the address page plus the load register pair, the first two instructions, into a more efficient instruction, like, for instance, the load register with a PC relative offset. So once we have our stencil generated at build time, here is, let's see how it is emitted at runtime. So this is actually the machine code bytes for setIP shown that is before the patching. These are generic instructions that still refer to symbolic addresses like JIT operand 0. Nothing here is executable until it's patched. Notice something important here as well. So this code is slightly different from the one that we saw in the previous slide. We have replaced the final jump to gContinue with a no-op. And that happens already during the stencil generation at build time, so when we compile CPython. This is because we just need to fall through the next micro-op without using any branch instructions, which would be more expensive to run. Then the JIT that patches the stencil with the runtime information by calling the function we saw earlier in the emit function. So the patch64, the memcopy, and the patch arg6433rx. And now we have the patch code in the executable memory. In this specific case, the JIT backend has rewritten the first two instructions to use a more direct addressing mode, replacing address page load register pair with a single literal load register. This is thanks to the optimization logic in patch ARC6433RX, which detects when we can relax the stencil, meaning we can generate a shorter and faster code because the operand fits in a simple form. After all these optimizations, the result is a smaller and more efficient native sequence. We have 2 actual instructions instead of the initial 4. And now it's ready to be executed. So where does this leave us? The JIT you've seen is real. It's in 3.14, and it's evolving quickly, but it's still marked as experimental. And this is what actually means. So performance, of course, are workload dependent. In some cases, the JIT can deliver up to 20% of speedups, but for others, you might see no benefits or even a small slowdown. There are also some important limitations at the moment, especially in 3.14. It's not compatible with the free threading yet. You need LLVM to build the stencils when compiling CPython, and there is currently no native debugger integration, so tools like GDB, Perf, or System Profiler cannot unwind through the JIT frames yet. Today, the JIT is supported on ARC64 and x86-64 on the 3 main operating systems, Linux, macOS, and Windows. There is also support for Windows 32-bit as well. So it's available in a lot of places, but it's not everywhere yet. So what's next? Looking ahead, the focus is making the JIT faster and more robust. On the performance side, we're working on various fronts. Just to name some of the efforts we have planned or happening, things are like reducing ref count overhead, top-of-stack caching, improving micro-optimizations, integer and float unboxing, and generate better stencils that produce a tighter native code. At the same time, we're also working to address the 2 big limitations we saw earlier, unwinding of the JIT frames to enable the native debuggers and compatibility with the free-threaded builds. So if you're curious, excited, or just want to experiment, this is the perfect time to get involved. You can already evaluate and test the JIT today, but just to be clear, don't use it in production yet. It's still marked as experimental, and we need the community help to fully validate it. So that said, here's how you can try. On macOS or Windows, the official Python 3.14 builds are already built in with a JIT, but it is disabled by default. So you need to enable the runtime, setting the variable Python JIT equal one, yes. On Linux, instead, you need to compile it, passing the enable experimental JIT flag. So once enabled in the sys module, you can have the _JIT module to check its state at runtime. Of course, if you run into issues, file a bug. If you see something unexpected or cool, share it. And if you want to have a better understanding how it works, the code is right there in the CPython GitHub repository. Personally, this is how I got started, by contributing, testing, reviewing patches. It's a great way to learn and be part of shaping what Python performance looks like in the future. As a last thing, I want to show a very simple but not so live demo of the JIT in action. So we have the same function that we analyzed during the presentation. It takes 100,000 as an input, and we run it for 500 times in a loop just to generate some workload. We firstly run it with the JIT disabled, and then we enable it with the environment variable Python JIT equal 1. As you can see, the non-JIT version takes 6.5 seconds, while the JIT version runs in about 5.6 seconds. So we get a 16% speed up in this case, just setting by the environment variable. So there are no code changes, no extensions. This is just by enabling the JIT in integrating CPython. Of course, this is a small example, but it shows that even a simple loop can benefit from the JIT. So these are a few references that I used to create this presentation. I'll leave it there for later consultation. And I think that's it from me. Thank you so much for your time. I hope this, thank you.